circuits. We talked last time about sort of the mechanism behind creating electric fields in circuits, talking about surface charges on wires and surface charge gradients. And I'm going to talk about now another tool for analyzing circuits. Okay, we've talked about the basic principle of the node rule or current conservation, saying the current in is equal to the current out of a particular point of a circuit. And so we can think of it as sort of one fundamental rule or fundamental principle to use when we're analyzing a steady state circuit. And another one we're going to be using is something we've seen before, is that the change in electric potential, if you go on a path that's round trip, okay, so your starting point is the same as your ending point, delta V round trip is equal to what? 0. Okay, so that's a fundamental rule behind potential differences. And we've seen this before, and so just to kind of remind you of how this works. So here is this actually isn't a point charge, it's actually a charged rod that we're viewing edge on, but you get the basic idea. And this red is a positive charge. And I can draw at various locations the electric field due to this positive charge, and it's going to be pointing away from the charge. And then I can think about a path, okay, choosing a path over which to calculate a potential difference. And if my path goes in the same direction of the electric field, I should get what sign for delta V? A little review here. You should go negative. Yes, you should go negative, right? Because remember that the basic, the most general definition is negative integral of E dot delta L, or you can think of that as sort of a summation of dot product of the electric field with the path over discrete increments, and you're just adding them all up if you're thinking about uniform fields over a short distance. And remember that the dot product says that if these vectors are in the same direction, then your dot product would be positive, but you have this leading negative sign out here, okay, because it's talking about the change in potential energy per unit charge, okay. So let me pick a path. So here's a path that goes in the direction, mostly in the direction of the field. And I don't know if you can read those numbers, but it's saying negative 11.3 and then negative 11.8 and negative 12.3. And then I'll choose part of a path that is mostly perpendicular to the electric field along that part. And so the potential difference really isn't changing that much. It's still around negative 12.2. And then I start moving in the opposite direction of the electric field, and we see that the potential starts to go down, right? Or the magnitude of the potential starts to go down. It becomes more and more positive because we're moving in the direction, or in the opposite direction of the electric field. So we're becoming more and more positive. So it's going from negative 11 or negative 12 to negative 4.7, negative 3.7 volts, negative 2.3 volts, negative 1 volt or so, about positive 0.7 volts, and then I'll just try to close off the path here, come back to where I started, and we go back to 0. And again, sorry if that's hard to read, but it is in fact saying dV, delta V is equal to 0. And I can even move the charge around a little bit, and we see that, so the colors on the different parts of the path indicates whether it's a positive or negative potential difference we're getting over that particular segment. And so if I've got a piece of the path, let's see, like around here, it's positive along here, negative along here, but again, the round trip potential difference gives you 0. And I can even go inside, and okay, fun stuff. But it's still, no matter how you slice it, you're going to get a round trip potential difference equal to 0, no matter what path I pick, right? I could pick a completely different path, something like that, and round trip potential difference gives me 0. So as long as I start at the same point as I'm ending at, delta V equals 0. So we can think about, say, sort of more of a dipole-looking pattern, because we're going to be talking about the field due to a battery, which we've talked about last time, and how a battery essentially maintains a charge separation And so we have positive on this end, negative on this end, and so the electric field here points away, electric field here points toward. And then in between, sort of like inside the gap of a capacitor, electric field, well, let's see if we can actually scale those vectors so we can see them. There we go. So I'm just changing the scale factor here so we can actually see these vectors. Electric field inside is pointing in the opposite direction, right? So, and then it kind of bends around like so. And then it starts pointing back towards the negative charge. So if I choose a path, say, that starts here, near the positive charge, and my path is mostly going there, it's got a component in the direction of the field, and so I'm getting more and more negative potential difference. It's up to negative 76, negative 80, negative 85, negative 90. But then I go through this capacitor, this in between the gap of the charge separation, and now my potential difference, or my path, I should say, is going in the opposite direction of the electric field. I'm getting more and more positive contribution to delta V, and then hopefully when I reconnect it, well, it's kind of close. It says delta V is equal to negative 1.1 because of computational inaccuracy. But you get the basic idea that if I'm going along the direction of the field here, I get a negative contribution, and I go in the opposite direction of the field inside that capacitor or that charge separation. I get a positive contribution to delta V. Sum them up, and it should add up to 0. It doesn't quite in this case because of inaccuracy. In fact, if I move that charge slightly away, it does give me a more accurate reading. It gives me, in fact, dV equal to 0. So this pattern, I show you this, why? Well, we're going to be looking at a circuit again. And let's actually draw just a simple circuit. So here is a battery. Okay, we just kind of draw a little cartoonish picture. We have a positive terminal of the battery, negative terminal of the battery, and just a wire. And so we can just think of this as a single wire, uniform thickness, connecting one end of the battery to the other. Okay, and let's call this location B and location A. And we know that, again, a battery just is maintaining a charge separation. So, in fact, let me even draw this kind of like we drew our picture last time. We were looking at the example of finding the charge distribution on the wires. Say we have a positive plate, positively charged plate, and a negatively charged plate. Okay, something like that. So let's say we want to pick a path that goes round trip. Well, let's say it starts at, well, actually, let me reverse these because I want to start at A. So let's do the same thing as we did here. Let's start here and call that B. So we'll start at A and go back to location A. And location A just happens to be just outside of the positive terminal. Okay. If I pick a path that starts at A and ends up at A, no matter what path I pick, it should give me a round trip potential difference equal to 0. That means if I could choose a path that goes out of the circuit, okay, and back like that, right, or something that goes around here or back like that. And that's interesting, but it doesn't really tell me much about the electric field inside the wires of the circuit, which is what we're interested in if we want to analyze the current and analyze the potential difference along the lengths of the wires of the circuit. So instead, I'm going to pick a path that starts at A, goes through the wire, goes to B, then goes through the battery, and then back to A again. Okay, so we're going along in that direction. Well, I should draw the electric field everywhere along that path. And let's see. So let's say at a location here, or that's in fact, let's say at location A, just outside the positive terminal of the battery, what's the direction of the electric field inside the wire? Yeah, pointing that way, right? It's kind of, again, think of it like a dipole. It's got to be pointing away from the positive end. And at this point, the electric field is pointing how? Pointing down, right? We know that if we're in a steady state, that the drift velocity is equal to the mobility times the electric field, then that the current is N times A times V. So the drift velocity is following along, going the path of the wire, and so the electric field is going to be opposite to that. Okay, V is actually pointing that way, right? And here we have the electric field pointing that way. Okay, here the electric field is going to be pointing up. Okay, here the electric field is pointing towards there. And then inside the battery, how's the electric field pointing? It's going to be pointing in the opposite direction, right, from the positive to the negative. Okay, and it's actually going to be a larger magnitude, and so by rights I should draw the electric field. Doesn't matter if it goes through the plate. We're just representing a larger field vector. Okay. So I know the directions of the field along, and let's call this E of the battery. Just distinguish these: E of the battery and E of the wire. In the steady state, so we have a single thickness wire. What do I know about the electric field everywhere inside the wire? Okay, it's parallel to the wire. What about the magnitude? Should be the same everywhere inside the wire. What tells us that? How do we know that? Okay, the thickness stays the same, and therefore from what principle do we know that the electric field stays the same? I in is equal to I out, right? If I mean, just pick anywhere in this wire. At any point in the wire, the current has got to be the same. So I in is equal to I out. Well, we know that N, A, V, or just think of it as, or just 1 and 2 if you want to label them that way. N1, A1, V1 is equal to N2, A2, V2, or writing this in terms of the electric field, N1, A1, U1, E1 is equal to N2, A2, U2, E2. And it's the same material, so the N's and U's are the same on both sides of the equation. It's the same thickness, so the areas are the same side, or are the same on both sides of the equation. So the electric field should be the same everywhere in the wire, and it's got to follow the wire because it's driving the current in the steady state. Okay. So that means if I want to apply this, what we're going to call, if we call this the node rule. Sometimes this is called the loop rule because we're talking about, if I can spell, we're talking about going around in a loop, okay, picking some path that goes around in the loop. And so what do we have? We're going to start here, go around, and come back to our starting point. So I'm going to have sort of two pieces to this path, right? I'm going to say a delta V round trip is equal to 0. So I have the sum of, or the negative sum of, the electric field in the wire dot some delta L plus the electric field in the battery dot that delta L across. So this is across the wire, and this is across the battery. Okay. And really, and let me just emphasize this. Again, the most general form of this relationship between the electric field, so this is round trip, electric field and potential difference is that it's an integral, okay? And you can always do an integral, okay? It just so happens that we just said the electric field inside the wire is a constant. It shouldn't change. And if we're thinking about our path, if I'm choosing a path that follows the electric field, think about doing that dot product. the magnitude of the electric field inside the wire times the magnitude of the length of the wire times the cosine of the angle between the two vectors, right? That's what we mean by taking a dot product. Well, if my path is always following the electric field, what's the angle? 0, right? And so it's just going to give me E times the dl, or E times delta L. And if the electric field is uniform, that electric field comes out of the summation or comes out of the integral, which you can just say it's the magnitude of the field times the magnitude of the length of the wire. Okay, and that's a negative out front. And then we have to add that to same sort of thing, right? If we assume that this is kind of like a capacitor, the electric field should be uniform inside the plates. And again, my path is, well, in this case, my path is in the opposite direction of the electric field, right? So I'm going to get the battery magnitude times delta L across that length of the battery times the cosine of what angle? So what is it? 180, right? Because my path is now, if I think about traveling along this direction, when I reach the battery, I'm going in the opposite direction of the electric field. So we have a cosine of 180. And that whole thing has got to be equal to 0. Okay? So we get a sign, I'm flipping the sign here. If I get rid of this cosine 180, that becomes a negative 1. Okay? And I can divide by the sign here. So if we worked it out, we'd find that the electric field, as we would expect, the potential difference across the wire is equal to the potential difference across the battery, right? This is just giving us E of the wire equals E of the wire times the length of the wire is equal to E of the battery times the length of the battery. Okay. Now, again, interesting, but unfortunately we can't go much further with this. I mean, we could measure the lengths of the wire. Okay, the wire might be some distance long. We can measure how long the battery is. We can't actually get anywhere unless we know something about what's going on inside the battery. Typically we don't measure directly the electric field of the battery or electric field inside the battery, but we know something about essentially the work done by the battery on a charge. And so let's think about a charge moving through the battery. And let me draw the battery again. Let's draw it over here. Sort of a zoomed in picture here. So here's our positive terminal of the battery. Here's our negative terminal. Well, first of all, let's go back to this circuit for a second. What's the direction of electron current? So an electron here is moving in what direction? Towards the negative terminal. Electrons are negatively charged, so they would have to move away from the negative terminal, right? So the drift speed is that way, or the drift velocity is that way, and therefore the little I, the direction of little I is that way, okay? So electrons are traveling through the wire in the opposite direction of the path I drew. That's okay. The path is just some arbitrary closed loop I'm drawing to find the potential difference. The electrons are really moving that way, okay? So they move this way, and they come to the positive terminal, and they go from the positive to the negative. So here's an electron inside the battery, and it's moving that way. So that means there's got to be a force on it in that direction to drive it from the positive to the negative. Now we said that the electric field inside the battery is pointing that way. Okay. What's the direction of the electric force on the electron inside? It's got to be the other direction, isn't it? That's the direction of the electric force. So it's not the electric force that drives the charge through the battery. It's not the electric force that maintains this charge separation. It's got to be some other force. And this other force is sometimes called, well, in the book they label it FNC. Okay, NC meaning non-Coulomb. Coulomb meaning Coulomb's law, electrostatic forces. It's not due to electrostatics, it's due to something else. And depending on the nature of the system, that something else could be some chemical reaction, like in a chemical battery that's maintaining this charge separation. It could be we'll see magnetic forces that try to maintain this charge separation later in the semester. In a mechanical battery, kind of like that model we showed last time, you could just imagine sort of turning a crank. Okay, that's driving a conveyor belt, making charges go in the opposite direction of the electric force. Okay, so that means this non-Coulomb force is doing some work because the charge moves from one end to the other. I'll call this distance s. Okay, so if the charge moves a distance s, then the work it does is going to be equal to the non-Coulomb force times that distance s. And then we define something called the work per unit charge, or FNC times S over Q. That thing has a special name. We give it the name EMF. Okay, so what is an EMF? Let me rewrite it over here. EMF, so historically it stands for electromotive force. That's a bad name for it because it's not a force. It's a work term, or energy per unit charge. And so we can think of it as the work per unit charge done by the battery. Okay? Well, if this charge is moving at a constant speed, at minimum, this force has to be numerically or equal and opposite to the electric force. Okay, and so it has to be numerically equal to the electric force times that distance per unit charge. But the electric force times that distance, or the electric, if Fe divided by Q is just the electric field times that distance, that's just the change in potential across the battery. Okay, so the EMF for an ideal battery, meaning a battery where we can approximate any inefficiency or any thermal loss due to being equal to zero. So very little energy gets dissipated away. We're assuming that all the work done is being just going into driving the charge and not being dissipated away as heat, for example. Then in an ideal battery, we can just say that the EMF is numerically equal to the magnitude of the potential difference across the battery. Okay, so that means you can look at a battery, see what its voltage rating is. It's 1.5 volt double A cell battery or a 9 volt battery. You can say, okay, that's the EMF, and that EMF is going to be mostly independent of what's connected to the circuit. Okay, if it's a non-ideal battery, you get into some issues, but in the case of an ideal battery, it's just a constant. It's just the number. It's just how much work the charge is going to, or how much work the battery is going to do per unit charge, and it's independent of what's connected to the circuit. Okay. Once we know that, well, then we've got it, right? Because now I can solve for the electric field of the wire, because this part is essentially the magnitude of that EMF. It's the magnitude of that potential difference across the wire. And so I can solve for it. I can say the electric field of the wire is just going to be the EMF over the length of the wire. Okay, if this wire has a total length of capital L, then I'm just solving that round-trip potential equation for the unknown, which is the electric field of the wire, and I can figure it out. Okay? once I know that, I could figure out other things. I could figure out the current, the electron current, because I know that's N times A times U times E. Okay, so if I know the electric field in the wire, I can then figure out how much current is being driven in the wire. Given I know that given I know the area and the other properties like electron mobility and electron density. Okay, I see a lot of glazed looks. So let's try an example. This is, once you get used to doing a couple of these, they really aren't that difficult. It's just a matter of setting up the equations and turning the crank. Okay. Let's try another example. So you have a battery connected to two thick wires and a thin wire. And the thick wire has area A1 and length L1. There's two of them. Okay, A1, L1, A1, L1. And then the thin wire has area A2 and length L2. So the basic strategy is start by writing down the node rule. Start by writing, and then write down the loop rule. In other words, current conservation and what amounts to energy conservation. And then see if you can solve the system for any unknowns that you're looking for. Let's start with the node rule. Okay, we all should know this by now. How do we compare the current, the electron current in the thick wire to the electron current in the thin wire? Okay, all right, well, this should be 100% by now, folks. Okay, this isn't that difficult. We've been harping on this for quite a while. So if you don't know this, you're going to have to. Okay, you're going to have to know it for the test coming up in a week. So be sure you understand this. The current in the steady state, the number of electrons per unit time that go past the point in the circuit, it's got to be the same going in as the same going out. So, here's a node, right? A junction between one wire and another. The current going, and by the way, which way is the electron current going? It's, that way, right? Electron current's going that way. Conventional current's going the other way, all right? So, but whichever. Electron current's going this way, so here's I1 and here's I2. And in the steady state, we've got to have the same number going in as going out per second, so I1 is equal to I2. So that can tell us something about the relationship between the electric field in the thick wire and the electric field in the thin wire. We have N1, A1, U1, E1 is equal to N2, A2, U2, E2, just substituting in the relationship between current and electric field into that equation. N is the electron density. Is that the same for these? If they're the same material? Yeah, that should be the same. Okay, so N1 and N2 is the same. Same material, U's should be the same, right? Mobility should be the same. So that tells us that A1, E1 is equal to A2, E2. Which means already we know that the electric field in the thick wire is bigger or smaller? Should be smaller, right? So we have a small electric field pointing what direction? At this location, E is pointing up. Yep. So that's E1. That's E1. And in here, that's E2. Okay? E2 is going to be larger because we have a smaller area. Okay, that's the node rule. That's as far as we can go at this point. Okay, so energy conservation, or in other words, round-trip potential difference being equal to 0. See if you can figure this out. We know the EMF of the battery. The EMF is, again, the work done per unit charge, some positive number, okay? And it's numerically equal to the potential difference across the battery. So draw a path. Think about a path that goes round trip through the circuit. See if you can write out in terms of the electric field in the thick wire, the electric field in the thin wire, and the EMF, an equation that comes from the loop rule, round trip potential difference being equal to 0. I would suggest actually drawing the circuit, and then drawing the path you want to choose through the circuit, and drawing the field directions along that path, because we know that determines the signs, right, of those potential differences. Okay, so we're converging toward an answer here. 76% of us say answer number 3, which is correct. So good job. So how do we determine this? Well, again, you should draw the electric. First of all, pick a path. It's up to you. You could go clockwise or you can go counterclockwise. It doesn't matter. The relative signs will come out to be the same. You'll get the same equation. I like to go in the direction of the electric field in the wire. It just makes a little bit more sense to me. So I'm going to go that way. Okay, that's going to be the direction of my path. Okay? And in the steady state, I know that, again, the electric field is always pointing in a direction parallel to my path. So that's E1, and then that's E1, and so forth. And so I would have, well, let me just write it out. We have delta V is equal to round trip equal to 0. And so I'm going to have a delta V in wire 1 plus a delta V wire 2 plus a delta V in the second wire 1, which I'll just label that wire 1. It turns out to be the same, plus a delta V in the battery is equal to 0. Okay? So I'm going in the let's start with this first wire 1. I'm going in the direction of the electric field, and so will that give me a positive or a negative? Delta V will be negative, right? So the delta V across, basically from this point to this point, going in that direction gives me a negative. And the field is, so I would have, a negative. And we're taking an integral here, but that electric field is uniform, so it can come out of the integral. So it's really just looking at the electric field times that distance. And so we have the magnitude of E1 times that distance, which we call L1. Okay? And then I go across the thin wire, and I'm going in the direction of the electric field. So that's going to give me negative. Okay, negative magnitude of E2, and I'm getting tired of writing that magnitude signs, so I'll just write them E1 and E2. So E1 without any symbols on it just means a magnitude. E2 without any symbols on it just means a magnitude. E2L2, okay? And then I have another length of wire 1. I'm going in the direction of the electric field, so the difference is, again, positive or negative. Negative. Same electric field magnitude as before, E1, and same length, L1. And again, they're in the same direction. Cosine of 0 gives me 1. So it's just the field times that direction. And then if I go across the battery, again, the electric field inside the battery is in that direction. So I'm going in the opposite direction of the electric field. So I should get a potential difference that is positive. And then we say this delta V across the battery is just numerically equal to what we call the EMF. Okay? And then I'm back to where I started from, so I set the thing equal to 0. And I have two terms here that are alike, so when I rewrite this, I have EMF minus 2E1L1 minus E2L2 is equal to 0. Okay? So now what do we have? We have, well, first of all, questions. Are we okay with this? Okay. Again, watch the signs. Okay, you've got to have, you could have gone the other direction, right? I could have gone in the direction of the electric field of the battery and in the opposite direction of the fields in the wire. That would have given me a negative EMF and a positive E1L1 and a positive E2L2. So all I'm just doing is multiplying both sides of the equation by a negative sign, and that doesn't change anything. The other side is 0, so that doesn't change anything. So either way doesn't matter. Okay. Can't say 1 or 2 because you have two different electric fields inside those wires. Okay. E1 is different from E2 in the second length, so it's not the same field. So you got to be careful about that. Okay. Let's try calculating something. We have two equations. I don't know the electric field E1. I don't know the electric field E2. So they're my unknowns. I have two equations and two unknowns. So this is a system we could solve. If we give the battery EMF as, say, 1.5 volts, the electron density, this is kind of a typical electron density for a metal, 9 times 10 to the 28th electrons per meter cubed. This is the mobility of a typical metal. It might be even be for copper or something like that. U is 7 times 10 to the minus 5 meters per second divided by volts per meter. We'll say length 1 is 0.2 meters, length 2 is 0.05 meters. Cross-sectional area 1 is 9 times 10 to the minus 8. Cross-sectional area 2 is 1.5 times 10 to the minus 8. Take a couple minutes, see if you can work out the magnitude of electric field E2, the field in the thin wire. If you're still working, that's okay. Let's see if we can try to set this up. We have we want to find E2, right? So I'm going to take this. I'm just going to do a substitution. I'm just going to take this equation, solve for E1. So it gives me A2 over A1 times E2. And then I'm just going to plug the result into equation number 2, right? So I'm going to have the EMF minus 2 times this result, A2 over A1 times E2, all times L1, minus E2, L2, and that's equal to 0. I'm going to factor out E2 as the common term here, so I have a minus E2. Actually, factor out a negative sign as well. So I have 2 A2 over A1 times L1 plus L2 equal to 0. And then I can bring the EMF to the other side of the equation, and then this becomes positive, and that equal to EMF, right? And then I can solve. I can say E2 is equal to the EMF over 2 A2 over A1, L1 plus L2. And finally, I have 1.5 volts over 2 times the area 2 is 1.5 times 10 to the minus 8. And area number 1 was what, 9? Got 9 times 10 to the minus 8. And L1 was, how long was wire 1? 0.2 meters. And then plus, what was L2, 0.05? 0.05? Okay. Okay. So what do you get? What do you do when you do all this? What do you get? You get 12.6? 0.1166? 12.6? Okay. Double check the arithmetic, right? Okay, we need to figure out a lot of things that you need to take into account here. Don't forget parentheses when you're doing, oftentimes when you're doing these long calculations on a calculator, break it up into steps, find this part first, then add that part, then invert it, then calculate that one. Okay, we'll pick this up next time.